Welcome back to QuantPy, guys. We are now going to derive the valuation or pricing PDE under the Heston Stochastic Volatility model. As we indicated in the preview on the Community tab, it uses the same concepts that we discussed when deriving the Black-Scholes PDE using the delta hedging argument, but things are slightly more complicated here because the underlying stochastic process is more involved and also because we are in incomplete markets. But on the bright side, we shall learn a couple of new tricks, or shall we say, a couple of new problems. The stock price is again assumed to follow the geometric Brownian motion, but the volatility, which was a constant in the Black-Scholes, is now itself a stochastic process. Heston assumed that the variance follows the square root diffusion with mean reversion mechanism. This is the same process that we saw when we were discussing the CIR short rate model, right? The two Brownians are assumed to be correlated with the constant correlation equal to rho, and we need the bank account as in the Black-Scholes, which grows deterministically at a constant rate r. We know there are good reasons for why Heston assumes these dynamics, right? It uses stochastic volatility because the Black-Scholes assumption of geometric Brownian with constant volatility is not consistent with what's observed in the markets. The return distributions have fatter tails and taller peaks compared to the normal distribution. The volatility implied by the option prices vary by strike. This is the so-called smile curve, and the shape and level of the smile curve varies by maturity. Making the volatility stochastic changes the properties of the return distributions and generate the smile effects, amongst other features. This is why Heston assumed volatility is stochastic. The correlation gives you control over the relationship between the volatility and the stock price. For example, we frequently see that markets are more volatile in bad times. You can get that feature by setting the correlation to a negative value. The correlation also affects the skew, so you can use it to generate the skew effects as well. The mean reversion mechanism is there because volatility is usually mean reverting, and the square root process is used to avoid negative variance. By the way, the variance process has several parameters: long-term variance or long-term volatility, mean reversion, volatility of volatility, etc. So it's usually hard to attribute each effect produced by the model to individual parameters, which complicates the calibration as well. But otherwise, the model is analytically quite tractable. And the holy grail for the modeler is to have a model that produces an analytical formula for the prices of options and also captures what's observed in the market. So this is what Heston was after, right? The holy grail. So the model is trying to capture what is usually seen in the markets using an analytically tractable framework, though it doesn't account for every possible pattern and behavior. For example, this being a diffusion model will struggle to explain the relatively steep skew seen in the volatilities of the shorter maturity options. Also, the model has a very limited number of parameters, so it won't fit or reproduce the entire surface. Hence, in practice, it needs to be decorated with a jump process to produce the steep skew in the short tenors, and or with the local volatility to fit the initial prices. Such a model would be called local stochastic volatility with jumps, but then it would be competing with other alternative specifications, but there's a topic for another day. For now, we are interested in only one aspect of the Heston model, this to derive the pricing PDE. We will explore other properties of the model in future videos. By the way, read the article about Stephen Heston on Wikipedia. As you would expect, he studied maths and finance, worked in finance and now teaches finance, but he probably spends more time writing about gambling, the poker and blackjack kind of stuff. That's fine as long as he's not gambling it away, hey? Now let's say we want to derive the PDE, that the price of an option that we denote by V must satisfy. The price will of course be a function of time, the two processes S and V, and the other parameters such as strike, maturity and the interest rate. we will suppress the constant parameters to avoid clutter. This is the usual thing we do. We will also suppress the dependence on time to make the presentation clearer. Let's do the same for the other processes. Now let's quickly explain what's different compared to the Black-Scholes PDE derivation. And the Black-Scholes model, the stock price followed geometric Brownian motion with constant parameters and only one source of randomness. So we needed only one asset to remove the single source of randomness, and we were able to hedge the impact of the randomness on the option price via delta hedging. There was no arbitrage and the markets were complete, though the options were redundant as you could replicate them by trading in the underlying stock and the bank account. All that meant we had a unique martingale measure, a consequence of no arbitrage in complete markets. In contrast, in the Heston model, we have two sources of randomness, so we need two assets for hedging, and the hedging strategy will now be delta sigma instead of just delta. As the volatility is not a traded asset, the market is not complete, though there is no arbitrage, which means instead of a single equivalent martingale measure, we will have a space of such measures, and we will need to find a way to make a sensible choice amongst these measures. As you can see, in comparison to Black-Scholes, we will need to hedge two sources of risk, and we will need to choose a measure out of many possibilities. The first part, which is the hedging, is going to be kinda a two-dimensional version of the Black-Scholes PDE derivation, whereas the second part will involve some discussion of martingales. So we are going to need some concepts that we discussed in the derivation of the drift under the risk neutral measure video. But if you haven't watched the video, that's going to be fine, as we are not going to rush anything here. First, let's see how the option price changes over a small period, for which we need our friend Ito's lemma. We need the two-dimensional version of the lemma. We have seen the one-dimensional version with time dependency before. For two dimensions, we add the first and second derivative terms with respect to the second stochastic variable, which is the variance process, and then the cross term between the two processes. So two-dimensional version of Ito's lemma is quite intuitive. We leave ds unchanged and substitute for ds squared. We know ds squared will be just square of the diffusion coefficients times dt. We do the same for v, leaving dv as it is, and substitute for dv squared, which again is just the square of the diffusion term times dt. And we then substitute for ds times dv, so you multiply the coefficients of the two diffusion terms, and dz1 times dz2 is equal to correlations times dt, so we get. Now we combine the dt terms, and we are left with two stochastic terms. Now to save space, we can abbreviate the differential operator and represent it by L. So we can write the drift term as L times V, which means the differential operator applied to V, and the three variables in the brackets capture the arguments. So the application of the differential operator to V is producing a function of the three parameters, yeah? This is more or less the standard notation for writing the operator, and is very similar to the concept of operator in algebra. Hiding the details has made the equation easier to write. Remember, V represents the price of an option, let's say of maturity T1. Now we're going to find a way to remove the randomness from the option price. Two sources of randomness, so we need two assets. One is the stock price, as in the Black-Scholes, and for the second, we will assume that we know the price of another option of maturity T2, which is assumed to be greater than T1. The change in the price of the second option will again be given by the same Ito's differential. So we are trying to hedge the risk of the option of maturity T1 using the stock price and a longer maturity option. The longer maturity option is needed so that we can hedge the option all the way to its maturity. though this can be done using other options as well. So we want to construct a portfolio of delta units of the stock, sigma units of the second option, and alpha units of the bank account. Remember, in the Black-Scholes, we discussed three alternative ways of constructing this hedging portfolio, but here we will just use the textbook approach. As we know, all roads lead to Rome, though I hear you say some are quicker than others, but I'm going to leave it to the Romans. Now, using the self-financing concept, we can write the change in the value of the portfolio as follows. Remember, we explained why we don't need to include the other terms that an application of Ito's lemma will produce. Essentially, the change in the value of the portfolio is coming from the price changes only, as the holdings are held constant infinitesimally and then rebalanced after the prices have been observed. We have the equations for dV and du, and we know dB, which is the change in the value of the bank account, and which is given by this equation. So substituting these three expressions, we get. Now we combine the ds terms on the right hand side. Now the stochastic terms are ds and dv. We can split these terms into the deterministic drifts and diffusion terms like we did in the Black-Scholes PDE video, but this isn't necessary and we will try to remove the whole ds and dv terms. To remove ds, we equate the coefficients of ds, and we do the same for the coefficients of dv. We can then solve this expression for sigma. Similarly, we solve the first expression for delta. We can substitute for sigma, but let's leave it as it is for now. Now we substitute these expressions for delta and sigma on the right hand side of the main expression. We just substituted the underlying expressions. Now the sigma terms cancel. Similarly, the partial derivatives of u cancel, and we get a much simpler expression. Now we can spot matching terms on both sides, which we cancel. So the terms containing ds cancel, and the terms containing dv cancel, and we are left with only deterministic terms. Now to see the rewards of our hard work, we just need to get rid of the bank account by using the replicating portfolio expression, and we will begin to see patterns. Remember, we use this portfolio of delta units of the stock, sigma units of the longer maturity option U, and alpha units of the bank account to replicate the option V. Now we need alpha times B, so we can isolate this term on the left hand side. We substitute for delta and then get rid of the brackets. We can substitute this expression for alpha times B into the main expression. Now every term has got dt, so we can get rid of dt and shift the terms containing V, the option price whose PDE we are after, to the left hand side. Now we factor out sigma on the right hand side, where I also swap the positions of the last two terms so as to align the expressions on both sides of the equality. Now we can substitute for sigma. We then shift the partial derivative of V to the left hand side to get. Now you see the expressions on both sides are the same. The left hand side contains V and not U, and the right hand side contains U but not V. It means the fraction must not depend on V and U, but it certainly depends on the parameters. So we can say it must be some function of these three parameters. We're ignoring the constants here, by the way. We write minus sign for reasons that will become clearer in a bit, but nothing will be lost if you decide not to put the minus sign in the front. It will find its way back in somehow. Now we can shift the denominator to the right hand side to get. By the way, we could have equally written this relationship in terms of the price of the second option, which is U, but remember we are interested in the PDE of V, so we naturally choose V. Now we have the result, which we just need to interpret. A lot is revealed if you shift the partial derivative with respect to S to the right hand side. Remember, R times S is the drift of the stock price SDE, so F must be some sort of drift of the variance SDE. It's an arbitrary function, but that doesn't mean we shouldn't try to find a sensible expression for the function F. Let's see our thinking informally at high level, and we will then dive into the details, which are very pleasant, but then you're not expecting me to say otherwise, right? We saw the dynamics of the stock price under the Heston is given by the geometric Brownian SDE with mean mu and variance given by the following SDE. Now, if the risk-neutral measure were to exist, then we know from the previous videos and a lot of other sources that the drift of the stock price will be equal to R times S. So the stock price SDE will become, where the Z to the power Q represents the Brownian motion under the risk-neutral measure Q. Now to see the link between the drift under the physical measure and the drift under the risk-neutral measure, let's rewrite the drift under the risk-neutral to reveal the underlying machinery. This complicated looking expression is equal to R, by the way, which is easy to verify. The square root of V cancel and the mu's will cancel, so the expression is indeed equal to R. But we can now see the link between the two dynamics as we have mu present here to speak for itself. By the way, this expression is just an application of the Kirsanov theorem that we discuss in the SDE playlist. Now this ratio term is axis return divided by volatility, or what the CAPM, which is the capital asset pricing model enthusiast, would call market price of risk. So if we represent its equivalent expression in the variance SDE by lambda, then to get the drift of the variance SDE, we will just need to adjust its drift by lambda times the volatility of the variance SDE. So we get, the reason we have to go for this alternative specification of the drift is because volatility is not a traded asset, so we can't write the drift as equal to R, the risk-free rate. Hence this expression is the equivalent of R times S, and thus we propose to set the function f equal to this expression. Now if we substitute this expression for f, and then recall that L represents the differential operator, and then substitute this for L, we get the Heston PDE. Oh, not too fast, I hear you say, so let's go through the promised journey. Did we say pleasant? To see the detailed justification behind the expression for F and the market price of risk. We know the two Brownians are correlated. Now let's try to express this system of equation in terms of non-correlated Brownians, which we represent by B's. We set Z2 equal to a standard Brownian motion B2. We then set Z1 as equal to a linear combination of the two independent Brownians. This is because Z1 and Z2 are correlated, but B1 and B2 are not by assumption, so defining Z1 this way helps us preserve the correlation structure of the system. Now Z2 is Brownian by definition, so that's fine. The properties of Z1 are also that of Brownian, as we can easily verify. The mean is 0 because the mean of each of the B's is equal to 0. For variance, we know B1 and B2 are independent, so the variance of their sum is equal to the sum of their variances, and we know taking the constant out of the variance operator involves squaring it. As both B's have the same variance because they're just standard Brownians, so the row squared terms cancel, and we see the variance of Z1 is equal to the variance of a standard Brownian. Similarly, it's easy to see that the correlation of Z1 and Z2 will be equal to the product of the coefficients of dB2, as dB1 times dB2 will produce 0 because they are independent, right? So we conclude that Z1 and Z2 so preserve the properties of the system. Now we substitute dB2 for dZ2 in the variance SDE, and the expression for dZ1 and the stock price SDE. So the system is now in terms of two independent Brownians, which is easy to handle. We rearrange the stock SDE, essentially shift S to the left hand side and get rid of the brackets. This is just to facilitate some algebraic manipulations, nothing serious. Now remember, in the Black-Scholes settings, the stock price follows geometric Brownian SDE with the constant coefficients under the physical measure. We saw that the dynamics under the Riesz-Newton measure are given by the same SDE but with mu replaced by R. BQ, as we mentioned before, represents the Brownian motions under the measure Q. And we also saw in a previous video that the two Brownian motions are linked as follows. You can easily verify the validity of this expression by using this expression to write the Brownian under the physical measure in terms of the BQ, which is the Brownian under the Riesz-Newton measure. Getting rid of the brackets, we get the mu's cancel and we get R as claimed. Now this mu minus R divided by sigma is the market price of risk, as we mentioned before. So if we represent it by lambda, we get. Now we can substitute for the Brownian using this alternative expression and we get. Now combining the dt terms, we get. So the equivalent of R is a mu minus market price of risk times volatility. This alternative form is used when markets are not complete or when the assets are not traded, which is the case for our variance process. So we can write B2, which is the source of randomness in the variance process, using this form. As volatility is not a traded asset here, this lambda is not unique, so this is why we represent the magic Q with lambda. So in a sense, we are saying that our magic Q depends on lambda, and corresponding to each lambda, there is an equivalent martingale measure. For the stock, which is a traded asset, we can write the relationship between the two Brownians using the previous form in terms of mu and R that we saw before. But here, the stock price SDE is the second Brownian, which is the one we said is non-traded, so we need to factor that in. The ratio here looks slightly complicated compared to the Black-Scholes, but the denominator is just the coefficients of B1, so it is the equivalent of sigma of Black-Scholes, and the additional term in the numerator is just the coefficient of B2 adjusted by the lambda. The main reason behind this form is that if we plug these for dB1 and dB2 into the stock SDE, the drift will be equal to R, which is the risk-free rate, which is what we want, right? Let's see it in action. Substituting for dB1 and dB2 into the stock price SDE, we just substituted these two expressions into the SDE just above, right? We get rid of the brackets. Now we just combine the dt terms, so we get, and all the terms other than R cancel, and the drift is indeed equal to R. So now you can see the complicated looking expression is doing the right thing. Similarly, we can substitute for dB2 in the variance SDE, and combining the dt terms, we get the variance SDE under the new measure. The stock price has two independent Brownians. Remember, we introduced these so that we can analyze the system in detail. Now we can go back to Z, so we just write the linear combination of the two Brownians as Z. We can see from the earlier discussion that Z will have zero mean and variance equal to that of a Brownian, so it is a Brownian, though it is now correlated with B2, which is the Brownian in the variance SDE, and this is what we want. And for easy comparison with the original case, we can replace B2 by Z2 as well. So we have the system in the original form, but the advantage now is we can pretend that conditional on lambda, we are in a risk-neutral world. Now remember, in the Black-Scholes world, the stock price SDE had the drift R under the risk-neutral measure. We saw that the process is martingale under the risk-neutral measure, and to price an option whose payoff function at maturity is a function of the stock price at maturity, which we represent by H, we can use the martingale property to say its price today is the expected discounted value of the payoff. Notice we have written the expectation as conditional on the initial value of the process instead of the filtration. This is because of the Markovian property, right? We saw that the price function also satisfies the Black-Scholes PDE, which you can derive via delta hedging, but this relationship between the expectation and the PDE is more general. Essentially, this is what the Feynman-Kac theorem is all about. In the present case, we are in the risk-neutral world, so we can write the price as discounted expected value, though we condition on the two variables now. So the PDE will be given by the two-dimensional version of the Feynman-Kac theorem, which is easy. We take the Black-Scholes one-dimensional PDE and add the first and second derivatives with respect to the second process and the cross term. We can rearrange the terms to give it some order, and then it will be easy to recognize the equation. Let's rearrange the stock price SDE to the same form as the variance SDE. Now it's easy to see that the Heston PDE is a two-dimensional version of the Feynman-Kac PDE, which is as follows. So the axes represent the underlying processes, and Heston we have two processes, so we call S x1 and V x2. Then it's easy to relate Heston PDE to the general Feynman-Kac PDE. Sigma 11 is the variance of the stock price SDE, sigma 22 is the variance of the variance SDE, and sigma 12 represents the covariance of the two SDEs, and it's easy to see that mu1 is the drift of the stock price SDE and mu2 is the drift of the other SDE. So easy peasy. Also, we know there is a close connection between the market price of risk and the CAPM type factor models. So you will also sometimes see the mu's written in terms of beta and factor risk premia. We will cover these connections in a future video, but let's see the results informally. Let's isolate the mu terms on the right hand side to allow for easy comparison. So if we assume a multi-factor version of the CAPM model, then we can also write the drift adjustments in terms of beta times the factor premia. The summation over f means one such term for each factor. Here mu p represents the original drift, which is now adjusted by beta times the market risk premia. And when we have a traded asset, this term becomes r, as we saw before. Now that we have the PDE, solving this PDE subject to the appropriate boundary and terminal conditions will give us the price of the option. Alternatively, you can also use Monte Carlo to price options as always. Additionally, the Heston model is analytically quite tractable, so you can also get a closed form expression for the price of European options, though it is in the form of a transform. We will explore these related topics in the future videos. We hope you enjoyed the video and we look forward to seeing you in the next.